Assalamu alaikum. Last week we had discussed sampling and its types. After this, we have recovering of the analog signal. So once we converted an analog signal to digital for a transmission purpose, then at the receiver we need to recover this digital signal, convert back this digital signal into analog, and then recover this analog signal. So one way of recovering the original signal from sampled signal x of s f is to pass it through a low pass filter as shown in figure. So when we convert an analog signal into digital, its output could be like this, where you can see the multiple samples of the same signal. It's spaced at different frequency, uh, from minus bandwidth to bandwidth and FC to FC plus B and minus FC minus B to minus FC plus B and so on. They will keep continue. So we use a low pass filter that will filter out the only bandwidth that we are looking for. In this case, it is from minus B to B. If sampling frequency greater than twice of the bandwidth, then we recover x of t exactly. As you can see here, the sampling frequency should be set greater than twice of the highest frequency component present in the analog signal. Then we can recover x of t exactly as you can see here. Else we run into some problems and signal is not fully recovered. Those problems are these symbols will be okay. Is anybody else having issue in our slides are not being shared with them? As it from my side, slide is already shared. Okay. Then 49, it is your side. You have some issue. Uh, Everyone else is can see the slides. So maybe your internet is slow, but at my end, I don't see any problem as I've shared the slide. You can download the slide from the Teams and look it locally, uh, hear my voice and see from your local file, local PPT. You can download it from the Teams. Okay, so I'm saying that when we start doing sampling, I told you that sampling frequency should be greater than the twice of bandwidth. That means oversampling. We should do oversampling to avoid any problems if we don't want to face any such problems at the receiving end. If we do the exact sampling, that is sampling frequency should be equal to twice of the bandwidth, then at the receiving side, we may have some aliasing effects. So to avoid any aliasing effect, we should use sampling frequency way greater than the twice of bandwidth. And this twice of bandwidth as a B term is in itself is confusing uh, because it is not the actual bandwidth. The bandwidth may be the power of the most of the signal may lie in lower frequency, but if there will be any single component there may be in such a high frequency component that is away from the actual uh, spectral, what say you can spectral efficiency frequency, then we have to count that. Like in voice communication, we know that the actual bandwidth of voice is in between 300 hertz to 3400 hertz, but we keep it like 4 kilohertz because this 700 hertz is like a margin. There may be a chance that someone voice means thousands in one, or maybe very low probability that a person has a voice whose frequency component may be in between 3.4 to 4 kilohertz. So this B term is actually the highest frequency component available in the signal. Twice of that frequency is should be your sampling frequency should be greater than that. Then we can recover the original signal easily. So undersampling and aliasing, if the waveform is undersampled, that is sampling frequency is less than twice of the bandwidth, then there will be a spectral overlap in the sample signal, as you can see in the figure. So we have undersampling, that means we have taken sampling frequency that is less than the twice of the highest frequency component available in the analog signal. Then there will be a spectral overlap. That means one sample will be in another sample's frequency. So that effect is called your aliasing effect. So the outcome of undersampling is your aliasing. That means we cannot recover the original signal properly. This happens when we choose less sampling rate than the twice of the highest frequency component. So this may be the case when we may have chosen sampling frequency exactly equal to 8 kilohertz or less than 8 kilohertz. And there is a frequency component available in the signal whose frequency is like 4 kilohertz or 3.8 kilohertz or 3.9 kilohertz. However, the sampling rate is said to be like 4 kilohertz. That should be in that. But due to some spectral broadening and something else, the actual frequency may move above 4 kilohertz. It may be 4.1 or 4.2, but we have sampled the signal according to 4 kilohertz. And due to spectral broadening in the analog signal, it may look like 4.1, 4.2, or maybe higher frequency signal. So when we do the exact sampling twice of the highest frequency component, that we considered 4 kilohertz, and due to spectral broadening in the analog signal, there may be some aliasing effect. So it is better to be on the safer side, so that f of s should be chosen greater than twice of the highest frequency component. It should not be equal, it should be greater than. At least you will have a margin of 400-500 at least, so that aliasing can be avoided. So the signal at the output of the filter will be different from the original signal spectrum. So when you recover, so it will be like this is the part that you will recover, but this signal will be cut here and it will be like this one. So you want to cover this one, this will be like this one, and then you will move like this one and it will go like this, and it will again come back like this. So that is seen here. So this is the signal that you have recovered if there is any aliasing. So this implies that whenever the sampling condition is not met, an irreversible overlap of the spectral replicas is produced, and you cannot fix it because you have already done the sampling, and now this is the signal that you are getting, and it is not same signal that you have transmitted. So that's why we say it's the irreversible overlap that you cannot fix with any other means. So better to use oversampling rather than the equal sampling. So this is the same figure in a different way, as you can see here. So this is your S of F, that is the continuous signal spectrum in the frequency domain. And you can see this drop to the FM is the maximum frequency component, and this is the sampling frequency that you have chosen. Now, if this is the case, then there will be no overlap because the two frequencies are way far from each other. So the maximum frequency component is here, and f of s is your sampling frequency here. But if there is another component that is alias component, so it will be into this component, as you can see in the next figure. So this is the part where these two signals, continuous signals, are overlapping with each other, and this is f minus f of m, and this is your f of m, and this is your f of s, and this particular part is in between f of s minus fm and f of m. So highest frequency will be fm minus f of m plus f of m. So this is your difference of sampling frequency here that will be overlapping the two components. Now this could be due to x of t containing higher frequency than were expected, an error in calculating the sampling rate under normal conditions. Under sampling of signals causing aliasing is not recommended. So it's one thing is very much established that if we do the undersampling, which is not recommended basically because it will cause the aliasing. So number two reason can be avoided by not doing the undersampling. So this thing has been established. But one says that x of t, that is your analog signal containing higher frequency component or higher frequency signal than were expected, means you were expecting that a signal x of t containing 4 kilohertz of frequency as the highest frequency component. So you sampled like 8 kilohertz or maybe 8.5 kilohertz, but there was one frequency component at 4.5 kilohertz. So in that case, your aliasing frequency that you have chosen at 8 kilohertz or at 8.5 kilohertz will not work. It will work, but you cannot recover the original signal because it will be overlapping. It will have the spectral overlapping, irreversible spectral overlapping, because you should have chosen 9 kilohertz as the some sampling frequency that you have chosen at 8 kilohertz or 8.5 kilohertz. So that one is like that. So this happened. So we always, when we convert an analog signal into digital, we should keep some margin frequency there in case if there is any frequency component present that is higher than the expected frequency, then it should not be affecting the output. So how to avoid these two things? Number two can be avoided easily. Uh, we must choose a sampling frequency that should not be undersampled. It should be oversampling. But what if how we can make correct measurements in x of t? How to band limit x of t? That is mentioned in the solution. All physically realizable signals are not completely band limited. Okay, so physically realizable signals means voice. They are not completely band limited. So if there is a significant amount of energy in frequencies above half the sampling frequency, aliasing will occur. Means let's deduce this one by taking some values. So assume that we have selected 8 kilohertz as the sampling frequency. Then half of that frequency will be equal to 4 kilohertz. Now this point says that if there is a significant amount of energy in frequencies above 4 kilohertz, then the sampling frequency of in 4 kilohertz, then aliasing will occur. मतलब कि जो आप सिग्नल ट्रांसमिट कर रहे हैं, जिसको आप कन्वर्ट करना चाहते हैं एनालॉग से डिजिटल में, उस सिग्नल में जो फ्रीक्वेंसी कंपोनेंट्स है, उनकी फ्रीक्वेंसी में जो एनर्जी है वो आधी सैम्पलिंग फ्रीक्वेंसी के बाद भी है, मतलब कि सिग्निफिकेंट एनर्जी है, मतलब सिग्निफिकेंट अमाउंट ऑफ इंफॉर्मेशन available in frequencies above half the sampling frequency, then aliasing will occur. So how we can prevent it? By first passing the analog signal through an anti-aliasing filter, also called pre-filter, before sampling is performed. And it is simply a low pass filter with cutoff frequency equal to the half the sample band. मतलब कि it's a reverse process. First you choose the sampling frequency, whatever you choose. Let's suppose we choose 8 kilohertz. Then you pass your analog signal that you want to convert to digital through a low pass filter by setting your cutoff frequency equal to 4 kilohertz. So there are two figures you can see. One is continuous signal spectrum and another one is sample signal spectrum, where you can see solid black lines. So these lines, solid ones, show you there is no overlapping. and the blue one shows you the overlapping. So aliasing is prevented by forcing the bandwidth of the sample signal to satisfy the requirement of the sampling theorem. So that is the filter that we use before the sampling, that we say the pre-aliasing filter, and it forces this sampling theorem onto the analog signal. As a result, you can have these black solid color output where you can see there is no overlapping. If this filter is not used, then you might have some overlapping, as you can see. So what are shown here? Let's see. So there is f of m, that is maximum frequency component. This is sampling frequency, and this is another sampling frequency which is higher than the actual sampling frequency. So one point is here, maximum frequency component, and this is your half of the sampling frequency, and this one is difference between sampling frequency and maximum frequency at this point. And this is f of s dash over 2 sampling frequency that is here. So see, the two sampling frequency that we have chosen, they are different from each other. So we should be choosing a sampling frequency that is greater than the actual sampling frequency. That means we are doing the oversampling. If we do the oversampling, then you have the solid black color output, which is not an overlapping. But if you chose the sampling frequency f of s as that is the actual sampling frequency, that is the twice of the maximum frequency, then you will have some aliasing effect, as you can see that we have the blue dotted line that shows you this effect. Now, when we do the cutoff frequency, we might have set this frequency as the cutoff, but the signal may, due to non-ideal nature of the cutoff filters, ideal filters are the real filters, जो कट ऑफ फिल्टर्स होते हैं आपके, सॉरी, जो लो पास फिल्टर होता है उसकी जो कट ऑफ फ्रीक्वेंसी होती है, उसका जो ड्रॉप होता है वो आइडल नहीं होता. हम उसको कहते हैं आइडियल लो पास फिल्टर्स, इन दैट इट इज वेरी sharp and it is perpendicular. But the real life low pass filters like Chebyshev and RC filters and other filters don't have that drop perpendicular. That is not very sharp or the ideal. We chose one frequency and the actual cutoff frequency and the chosen one will have some difference. So this red line shows you that difference. This we have chosen, and this is the actually it went up to this point. Then we say now f of m. If this happen again, then we will also have the overlapping in that regard. So this slide shows you deduce that whatever your sampling frequency or whatever your calculation suggests you to choose a sampling frequency, you must select some higher sampling frequency to avoid the aliasing effect. Solution 2 is oversampling and filtering in the digital domain. The signal is passed through a low performance, less costly analog low pass filter to limit the bandwidth. Sample the resulting signal at a high sampling frequency, like in the previous figure. Rather than sampling at f of s, we were sampling at f of s dash, that is the higher sampling frequency than the actual sampling frequency. Then the digital samples are then processed by a high performance digital filter and downsample the resulting signal. So that is another solution to avoid the aliasing In solution one, we suggest to use a pre-aliasing filter, that is a low pass filter. In solution two, and that filter will be costly. If you want to have that filter efficient, or you want that the actual cutoff frequency and the uh, such actual cutoff frequency should have less difference, then you should go with a high quality low pass filter. That will be expensive. But in this case, in solution two, the signal will be passed through a low performance analog low pass filter to limit the bandwidth. Means the analog signal will pass through this filter, uh, that may be set at 4 kilohertz. So you might have the actual frequencies pass through that maybe up to 4.2 or 4.3. So that is due to the non-ideal nature of the low pass filter. Then sample the resulting signal at a high sampling frequency. The reason is we are sampling now at a high sampling frequency because we know that in the first step we choose a low performance, less costly analog low pass filter, which might have a load few extra frequencies. To compensate that, we should be doing the high sampling. But in the third step, we can compensate that by using the high performance digital filter to filter out the digital samples, and we will downsample the resulting signal. So these are the two solutions that can be used to avoid the aliasing. So this is the summary of sampling. We have three types of sampling: ideal sampling or impulse sampling, natural sampling or getting, flat top sampling. Uh, that is the actual sampling that we do using the sample and hold mechanism. For all sampling techniques, if f of s is greater than twice of the maximum frequency component, then we can recover x of t. Exactly. If sampling frequency is less than twice of the maximum frequency component, then there will be select spectral overlapping known as aliasing will occur. So these are the like first steps when we convert an analog signal into digital, because we are learning digital communication. In digital communication, whatever the input signal is, we need to convert that signal into digital domain before transmission, because transmission is the digital signal transmission. So it's a try example one. Consider the analog signal x of t given by, so this is a combination of an few signals that is equal to one analog signal. So you can see there are different frequency components available in this signal. So if I ask you what is the Nyquist rate for the signal, what will be your answer? If x of t is equal to 3 cos 50 pi t plus 100 sine 300 pi t minus cos 100 pi t. So what should be your Nyquist rate or the sampling frequency if x of t is the given analog signal? Anyone? I repeat again, if x of t is equal to 3 cos 50 pi t plus 100 sine 300 pi t minus cos 100 pi t, if this is the given analog signal, then what is the Nyquist rate or the sampling frequency for this signal? Seems like no one knows the answer or you are not listening me. 600 hertz. How? 600 is the wrong answer, dear. 31. But anyway, good to know an answer from your side. Anyone else? For this given signal x of t, that is 3 cos 50 pi t plus 100 sine 300 pi t minus cos 100 pi t, what should be the Nyquist rate or the sampling? Yes, 300 hertz is the correct answer because the highest frequency component here we have the 150. This is 2 pi f of t. If you divide this one as with 2 pi f of t, you will know that f is 150. So f is 150. That is the highest frequency component available in this signal is 150 hertz. Then the Nyquist rate should be greater than or equal to 300 hertz. So the answer should be like it should be greater than at least 300 hertz. Then example 2, consider the analog signal xa of t given by xa of t is equal to 3 cos 2000 pi t plus 5 sine 6000 pi t plus cos 12,000 pi t. What is the Nyquist rate for the signal? And what is the discrete time signal obtained after sampling if f of s is equal to 5,000 samples per second? Third one is what is the analog signal x of t that can be reconstructed from the sampled values? So hurry up, everyone should solve this one. If you want today's attendance, as I am seeing that you have just joined the meeting. Now your few people are only responding, only 2 exactly. Others, I don't know what they are listening or not. 6,000 Nyquist rate for which example? Example 2 or example 1? Example 2, 6,000. No, that is the wrong answer, dear. 45 is the wrong answer. Example 2, Nyquist rate is 12,000. That's correct. Second one is what is the discrete time signal obtained after sampling if f of s is equal to 5,000 samples per second? So what about the second one? And then it asks you, uh, yes, 12,000 is for the second example. What is the discrete time signal obtained after sampling if f of s is equal to 5,000 samples per second? So instead of 12,000, if we choose f of s as 5,000 samples per second, what is the discrete time signal? So B and C, what should be the answers for B and C? Discrete time signal obtained after sampling if f of s is equal to 5,000 samples per second. And third one is 2.4. What is 2.4? Any unit? 2.4, 2.4 toffees, 2.4 biscuits, 2.4 people. What is 2.4? Ah, yes. 31 is correct. Second one. And 15,000 samples per second. So 15,000 is the answer for the third part, is it? Double one. Okay, seems like we done all three examples. Yes. Okay, move on. Then we have some practical sampling rates, speech, audio, video. Okay. Telephone quality speech has a bandwidth of 4 kilohertz. Most digital telephone systems are sampled at 8 kilohertz, 8 kilosamples per second. The highest frequency the human ear can hear is approximately 15 kilohertz. CD quality audio are sampled at a rate of 44,000 samples per second. Video, the human eye requires samples at a rate of at least 20 frames per second to achieve the smooth motion. So these are some rates that should be applied in daily life. Then we have another important topic, that is pulse code modulation. Pulse code modulation refers to a digital baseband signal that is generated directly from the quantizer output. Sometimes the term PCM is used interchangeably with quantization. Block diagram is given. So this PCM signal, basically a digital signal that is generated when we convert an analog signal through sampling, quantization, and coding. And that signal is called the PCM signal. Normally, when we say PCM, it is directly related to the voice signal. Basically, in cellular communication, PCM is used for a particular bit rate. Anyone knows that bit rate? PCM bit rate is equal to, what is the bit rate when I say PCM? A PCM is equal to dash bit rate. Almost all the carriers that we learn, you might have learned in the 7th semester, E1 carrier. 110. What is 110? Yes, 64 kilobits per second. That is the PCM. One PCM is equal to 64K bits per second. That is 64,000 bits per second. That we have when we convert a voice signal from analog to digital. Yes. Yes, 64 kilobits per second bit stream. So moving on with the PCM. Yes, 64. So these are the quantization levels that you can see in your figure. We have sampling is done in time, whereas quantization is done on the y-axis. That can be your ampere, that can be your voltage, means amplitude. And amplitude can be in any value. It can be power, it can be ampere, it can be voltage. But the commonly we use voltage is commonly used as the amplitude. So here you can see amplitudes are given in voltage form, and there are samples that we have chosen, like one sample, 2, 3, 4, 5, 6, 7. So these 7 samples are chosen on the x-axis. So these samples should be defined in time as well as in the voltage. So a sample should have two values, one in time and one in amplitude. So in time, it is very simple. We know that we have to convert a continuous time analog signal into like twice of the greater than twice of the maximum frequency components. Like if the analog signal frequency is 8 kilohertz, so there should be 8,000, more than 8,000 samples per second on the x-axis, so that we can choose the x-axis. But what about the y-axis? How to choose their values on the amplitude? What should be their amplitude? So when we say the amplitude, that we say the quantization level. So that is the amplitude level, that is their quantization level. How much information they represent using different voltage levels, and what information they represent using different voltage levels, that is known as the quantization. And the next step is the coding, that will tell us which information they carry. So as you can see here, this sample uh, taken on the x-axis has a value on the amplitude level. On the y-axis, actual value is 1.3. That is the natural sample value. That is 1.3 volt. But 1.3 volt is not available on the y-axis, because we have divided the y-axis or the amplitude in different levels from 0 to 4. They are divided from 0 to 0 0.5, 1 to 3, 3.5, and 4. So zero point 0.5 is the step size. After every 0.5, we have divided the amplitudes. So that means the step size can be reduced if we increase the number of quantization levels. At this time, we have maximum voltage that we have is 4. And we divide this 0 to 4 into 8 samples. Into 8 samples. That means 2 power 3. That is equal to 8. That means every sample will be represented by 3 bits. So see, we have now like 8 samples. That means 2 power 3. So every sample can be represented by 3 bits. So actual sample, the value of actual sample is 1.3, but 1.3 voltage is not available. That level is not there. So actual level is 1.5. So instead of 1.3, we have to choose 1.5. So that difference between the actual sample value and the available quantized sample value is called quantization error. So that is 0.2 voltage is the quantization error because the actual sample value was not there. So we have to be forcefully choose the 1.5. So as we increase the quantization levels, means we can go with 2 power 4, that is 16. Then it will be like 0, 0.25, 0.5, 0.75, 0.75, then 1, then 1.25, and then 1.5. So in this case, if we have 1.3 and if we use 2 power 4, that is 16 levels and 4 bit per quantization level or 4 bit per sample. Then instead of moving 1.3 to 1.5, we have to move 1.3 to 1.25. So that is a difference of only 0.05 instead of 0.2 volt. So that means the quantization error has reduced from 0.2 to 0.05 only by increasing the quantization levels. We further increase the quantization levels, we can we can reduce the quantization error. So, but by increasing the quantization levels, we are also increasing number of bits required to transmit same information. So we need more bits to transmit same information as we do with the less number of quantization levels. But there is a trade-off. Lower number of bits, but there is a higher quantization error. Higher quantization levels, but there is a less quantization error. So you have to make an adjustment or you need to make a trade-off or choose an optimization level that should do the both. It should not be higher quantization error. It should not be high number of quantization levels. Is it clear? So the rest of the samples also chosen at the different values. You can see actual value is 3.6, but it is transmitted at 3.5, 2.3 to 2.5, 0.7 to 0.5, minus 0.7 to minus 0.5, minus 2.4 to minus 2.5, and minus 3.4 to minus 3.5. And we have numbered them. The first sample is numbered as code 5. Second one is 7, 6, 4, 3, 1, 0. Then we have to convert them into their binary equivalence. That is 5 is equal to 101 on the 3-bit scale. 7 is 111, 6 is 110, 4 is 100, 3 is 011, 1 is 001, and 0 is 000. So every information or every sample of this particular example will be transmitted using 3 bits. And combinedly, we call that as a PCM sequence. Is it clear? This example 2.16. If you have any questions from this one, you can ask. If you have any questions up to this point, you can ask. Okay. Let's have a break of 5 minutes. We will continue after the break. Their attendance is recorded by teams. Your every whatever you say, क्या कहते हैं जो आपकी पार्टिसिपेशन है आप when you log in, when you log out, how much time you have spent in the meeting, everything is recorded. There is an app that record your every movement. So from there I can see your attendance, and then I have an Excel file where I record your attendance. That is how your attendance is being marked. ये डब्ल्यूसी का क्लास दो क्लास आज होंगी, दो क्लास मंडे को होंगी, और बाकी जो तीन क्लास हैं आपकी वो सैटरडे को होंगी। इज इट क्लियर? वायरलेस कम्युनिकेशन की क्लास की बात कर रहा हूँ। वायरलेस कम्युनिकेशन क्लास, टू क्लासेस विल बी ऑन मंडे फ्रॉम 8 to 9:30, and today it will be two classes from 11:30 to 2, and there will be three classes on Saturday. जिस टाइम पे वहां पे है मौजूद उसी टाइम पे होंगी, 11 बजे से मेरे ख्याल से, तो 11 बजे से होंगी 11 to whatever it is, 3 hours, three classes of 45 minutes. Don't know yet about the mid semester when it start. When I know, I will share with you. This is the same. You can say the states or the another figure to represent this figure. So this figure and figure 2.16 and this figure is actually same. There is no difference between them except here the PAM signal, pulse amplitude modulation signal, quantization and coding are shown as the separately, but actually these two figures are the same. Then advantages of PCM: relatively inexpensive, easily multiplexed. PCM waveforms from different sources can be transmitted over a common digital channel, that is time driven multiplexing. So as PCM is based on bits, so we can multiplex these bits from different uh, sources and we can transmit them onto a single transmission line using time driven multiplexing. Means in different time slots and frames we can transmit or multiplex multiple resources onto one. So that is how we make E1 carrier from this PCM. If we combine 31 PCM channels, we can have a single output of 2.048 megabits per second. And similarly, we can multiplex E1s, 4 E1s to make E2 that is of 8 point something megabits per second and so on. Then we have E3, E4 and the hierarchy goes on. Similarly, we have SDH where we combine 63 E1s to have 155.52 megabits by multiplexing in time. That is all those input waveform are the PCM waveforms. So due to this PCM waveform flexibility, we have high data rates. We can achieve high data rates by multiplexing multiple inputs through time-driven multiplexing, and we can get a high data rate. Easily regenerated, useful for long distance communication, example telephone, for other services, for other communications, for transmission, or even for long transmissions, SDH and STM1, other things are also used. So all basically based on this PCM. So it is easily regenerated and can be used for the long distance communication. Better noise performance than analog system, very because you can regenerate the digital signal. So there are only possibilities if we have the two-level binary signal that is 0 and 1. If it is bipolar, then there will be two voltage levels. So instead of analog signal, which has thousands of variations, a digital or PCM signal has only one or two variations, 2 to 3 variations. Signals may be stored in time scale efficiently. Efficient codes are readily available. Disadvantage requires wider bandwidth than analog signal because it's digital format, so it needs more bandwidth than the analog signal. Then we have the sources of corruption in the sample, quantized, and transmitted pulses. So I already told you quantization error or the quantization noise that results when quantization levels are not finely spaced apart enough to accurately approximate input signal, resulting in truncation or rounding error. So as we have seen in the previous figure, we go back this one where the actual sample value or the natural sample value is 1.3 and the next available nearest available quantization sample value is 1.5. So we have to take this 1.3 as 1.5. So this difference is your quantization noise or quantization error. Results when second type of quantization effect is the quantizer saturation or overload noise. That results when input signal is larger in magnitude than highest quantization level, resulting in clipping of the signal. Same figure we take as the example. So the highest voltage level present here is 4. Somehow this signal may be like greater than like 4 voltage level, maybe at 4.5. So there is no voltage level available at 4.5 here. So we have to consider this 4.5 as 4. So that means 0.5 voltage will be truncated or clipped. So that is another type of quantization error that can also occur, that's called quantizer saturation or overload noise. Timing jitter that caused by a shift in the sampler position can be isolated with stable clock reference. So this is a timing error, means your signal either be delayed or in advance. Due to that, there will be a shift in the sampler position, and that will cause the timing jitter. Where channel effects are the channel noise and the intersymbol interference. Intersymbol interference, as we seen, it's one of one of the types. Aliasing effects are the again type of the intersymbol interference, where one sample goes into the frequency of another sample. When it happens, it is very hard to recover the irreversible sample. The original signal, analog signal, is very hard to recover them. Then we have signal to quantization noise ratio. The level of quantization noise is dependent on how close any particular sample is to one of the L levels in the converter. As you can see here, different samples uh, are like far from the actual levels, like this one. So actual sample value is here, but the level is present here. So this is the error. Same is here, same is here, and same is here. So this quantization noise, we also say quantization error, is dependent on how close any particular sample is one of the elements. If it is very close, then quantization noise will be low. If the distance between the quantization level L and the sample is too large or is too much, then the quantization noise will be higher. For a speech input, this quantization error uh, resembles a noise-like disturbance at the output of a GAC converter. If the quantization mismatch, that means the actual sample value and the level are have a significant difference, then when we convert signal from digital to analog, we will see we will hear a noise disturbance at the output. Noise like disturbance at the output. Then we have quantization types. We have two. One is uniform quantization and one is non-uniform quantization. Let's first see the uniform quantization. A quantizer with equal quantization level is a uniform quantizer. Like we have seen in the figure that we consider the first one, this one. So this is the uniform quantization. As you can see, the difference between the lower quantization level and the next quantization level and the next quantization level is same. In this case, it is 0.5, 0 to 0.5, and then 0.5 to 1. So again, that is the difference of 0.5. So that is the quantization step. If it is uniform, then that type of quantization is called uniform quantization. In this case, the unit quantization step size is 0.5 and it remains uniform throughout. So that is uniform quantization. So each sample is approximated within a quantile interval. So that is a quantile interval from one level to another. So this figure is taken vertically rounded to horizontally. So this is the lowest level, like the first level. As we see, if you make an analogy with the figure, it is 0. This one is 0 volt. This one is 0.5 volt. And this one is 1 volt. Okay. So as we have taken center at 0, so that is same. This is 1 minus 1 upon 2, and this is plus 1 upon 2. So the quantization error cannot exceed Q over 2 or 1 over 2, whatever the Q is, and total is 1 over Q. So the quantization error will remain in between minus Q over 2 and Q over 2. It cannot exceed that. It is bounded by that. So each sample is approximated within a quantile interval. Uniform quantizers are optimal when the input distribution is uniform. So that is when all values within the range are equally likely. Most analog to digital converters are implemented using uniform quantizers, and error of a uniform quantizer is bounded by this expression that is from minus Q over 2 to Q over 2. Basically, that is a value of 1. If you keep Q as a constant, 1 over 2 plus 1 over 2, that is 1. It cannot exceed 1. And if you take the Q, it will be particular value in between, like in the previous figure, if you go back. So it is from 0 to 1 and then 0. So the maximum, so this is from here to here. So the maximum voltage difference is 0.5. So the quantization error cannot exceed 0.5. So in this case, it will be minus 0.25 to 0.25. Error cannot exceed minus 0.25 to 0.25. Why we say that? Because if a sample is exactly in between here, so that means at center of the sample, let's suppose the first sample that is from 0 to 0.5. So if a sample is here exactly in between the two quantile steps at 0.25, so we can either move it like 0.25 positive or minus 0.25 voltage negative. In that case, the error can be plus 0.25 or minus 0.25. But it cannot exceed 0.5 because the maximum quantile step is 0.5. So error will be less than 0.5 in any case for any of the distributions. Is it clear? Like here you can see. Okay, good. The maximum voltage is shown here is from minus VP to VP, that is a peak to peak voltage, VPP. And we divide this peak to peak voltage in L levels. And the first level is Q by 2, and the next is 3Q by 2. And the first level is from minus Q by 2 to Q by 2. That is 1Q, 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 and so on. So this is the figure that we have taken in the previous figure horizontally, or vertically to horizontally. If you go back, if you rotate this figure like this one, you will find this condition is same as this one. So this is the maximum uh, error that you can have from minus q by 2 to q by 2. That is our 1q. Okay. And this figure we like drawn like this in the previous, that is minus q by 2 to q by. So the maximum, this is the maximum error that we can have of 1q. Anyway, I stop here. We'll continue from here in the next lecture, that is tomorrow early morning. If you have any question, you can ask.